Hello, I'm Minaju from Team Kwix. In this KWIX, I will present our work on development of an SPPWM and performance improvement algorithm for driving a 5 HP induction motor. Our presentation is organized into 4 parts: topic and objectives, method and design, result, and discussion. Our research focuses on developing an SPPWM technique and quality improvement algorithm for driving a 5 HP induction motor. Induction motors are widely used in industry due to their high efficiency and reliability. They play a crucial role as essential power sources in automation systems and industrial machinery. So optimizing their performance is very important. In this study, we propose a method to improve voltage utilization and reduce harmonics using the SPPWM technique. However, in real motor circuits, data must be inserted, which can distort the output voltage. This becomes particularly important at low speeds, where the error depends on the current direction. Compensating for this effect is essential. To address this, we propose two compensation methods: a dynamic daytime compensation algorithm and a PR controller-based compensation algorithm. The dynamic method adjusts the output voltage in real time based on the rate of change of current, while the PR controller allows selective harmonics compensation for more precise control. By applying both, we aim for efficient speed measurement and improved output voltage quality. To implement these algorithms, we designed optimized hardware and firmware, conducted experiments, and compared the result with simulations and measurement from oscilloscope to verify the inverter's performance. The SPPWM technique models the output voltage of a 3-phase inverter as a space vector and generates switching signals accordingly. Compared to conventional sinusoidal PWM, it can produce a higher fundamental output voltage, improving voltage utilization under the same DC conditions. In SPPWM, we select the two active voltage vectors closest to the reference vector, and apply them alternately for short intervals to generate the desired average output voltage. 3-phase inverter switching states are divided into active and zero voltage vectors. Zero vectors occur when all switches are on or off, producing zero output. Active vectors occur when one or two phase switches conduct, producing 6 possible vectors that determine output voltage magnitude and direction. The voltage space is divided into 6 sectors, each with its own active vectors combination. Within a sector, phase voltages are classified as maximum, medium, or minimum relative to the DC link voltage, allowing precise calculation of T1 and T2 times for the active vectors. The PR controller exhibits very high gain at a specific frequency with no phase lag, making it suitable for harmonic compensation. In our approach, the PR controller runs in parallel with the current controller in the synchronous reference frame. By tuning the PR controller to match the 6S and 12S harmonics, it can selectively extract and compensate for those components, effectively reducing daytime-induced effects. The dynamic compensation method considers the rate of change of current. First, we diagram the current components inside the daytime depending on current direction. When the current is positive, the T2 vector seems to decrease. When negative, the T1 vector decreases. This defines the basic compensation formula, which is further adjusted by measuring the current's rate of change. Here, alpha acts as an adaptive coefficient based on system parameters. Simulation results show that without compensation, THD was about 5.4%. Both methods significantly reduced the 5s and 7s harmonic components. With PR controller-based compensation, THD dropped by about 57% to 2.31%, and the dynamic method reduced it by about 58% to 2.29%. Both are effective at reducing THD. Next, we built actual hardware to verify the algorithms. The inverter's main circuit, which generates switching signals, includes signal input, gate driver, MOSFETs, and current sensor. In the gate driver, galvanic isolation ensures stable output, while a bootstrap circuit and adjustable on-off resistance improve reliability. A bidirectional Zener diode prevents voltage surges, and Kelvin source MOSFETs maximize isolation from the power circuit. In the sensor circuit, we use an analog low-pass filter and buffer circuit to minimize input impedance. For hardware implementation, PCB structure is critical. With multi-layer boards, layer interference is inevitable, but proper layout minimizes its impact. We increased the distance between power and signal circuits and inserted ground planes in the middle layers for magnetic shielding. Ground planes were separated into 3 functional planes to suppress EMI noise. In firmware, the incremental encoder is attached to the motor shaft and has slots. Light passes through the slots and is detected to generate pulses. A and B pulses are 90 degrees out of phase, allowing determination of rotation direction. Pulse counts can calculate motor speed. There are 2 main methods for measuring speed with an encoder: the M method and the T method. M method counts pulses in a fixed interval group for high speeds with low CPU load. T method measures time between pulses, accurate at low speeds but sensitive at high speeds. The MT method combines both, M for high speed, T for low speed, enabling accurate and efficient speed measurement. In terms of firmware implementation, there are 5 key points. First, the system clock setup to ensure high speed and accurate operation. Second, a period interrupt-based control structure that separates control and speed estimation for reliability. Third, precise PWM generation using direct timer register control. Fourth, DMA-based ADC processing to reduce CPU load. And finally, DAC-based control signal verification for real-time monitoring and validation. These 5 elements together ensure accurate and efficient motor control. Here's the overall system block diagram. The MCU performs real-time vector control with daytime compensation, generating PWM signals for the inverter. The inverter converts DC link voltage to AC to drive the motor. Speed and 3-phase currents are measured and fed back to the MCU, enabling precise closed-loop control. Here is a demonstration video. When we input a speed command, the motor rotates accordingly. An FFT analysis shows that the fundamental voltage frequency rises with speed. Here are phase current waveforms and FFT graph from our custom inverter with different compensation method: no compensation, PR control-based, and dynamic compensation. Both methods significantly reduce main harmonics like the 5th and 7th, effectively reducing waveform distortion. In this study, through simulations and hardware tests, both methods effectively reduce THD, showing that the proposed strategies achieve meaningful harmonic separation in real system. PR controller-based compensation can be applied to various systems with binary adjustment, but encourages firmware usage and system complexity. On the other hand, dynamic compensation has low computational load and simple tuning, but is specific to 3-phase inverters and cannot directly apply to single-phase systems, since it is based on the concept of the middle phase current. Each method has clear pros and cons, so the choice should match the system architecture, target application, and available resources. It is important to choose the method that best fits the actual operating environment. The references are listed separately for each section. That's all for my presentation. Thank you for your attention.